and we'll talk about determinants again. So if you remember, last time we stopped at these properties of the determinant, those three properties which are here, and we exemplified those properties. Maybe we can, go over a few more exercises and problems before we move on and talk about some other properties. So let's see. I think I scanned the exercises from this section 3.2, and can you see them?
Yeah.
All right. So let's go over these exercises, one by one. At least, for the first group. So here we have each equation in this exercise illustrates a property of determinants. States the property. So for the first one, it looks like two rows. Let me see. Yeah, two rows are interchanged, right? So let's see, this row here is this one here, right? And then if I change a color, this one here equals this, is this one. So that was property, I think we called it B. It's like in the textbook. I try to stick with the the book in terms of labeling these properties. So this is B, right? What about this one? If you have the textbook, or if you have the notes, you should be able to tell me what property is used here. So what's done here? You see, look at this row. We can factor out 3, right? And then what's left is 1, -2, and 3. So for this one, it's property C, right? It says that if one row of a matrix is multiplied by K to produce another matrix, then the determinant of the produced matrix is K multiplied by the determinant of the original matrix, right? So this is property C, an illustration of property C. What about this one? What about this one? So how do we obtain this equality? You have to speak up. I'm not going to read, the chat or anything. So how do we obtain this equality?
Are the properties found in the book?
Uh-huh.
Okay, hold on.
So it's either A or B or C. So which one I should use here? So how do I get, you see, the first two rows are the same. How do I obtain the third row here and still have equality of these determinants? Look at the row 3. If I add to the row 3, actually if I subtract 2 times row 1, right? That gives me the new row 3, right? So this one. So I multiply the first row by 2 and subtract it from the third row. So meaning what property?
That's property A, right?
Very good. Yeah, it's property A. That's property A because you multiply by a number, -2, this row 1, and add it to row 3. Then you end up with this, right? You see that? -2 times 1 is -2, added to 2 is 0. Then you have -2 times 2 is -4, plus 7 gives you 3, this one. And then you have negative 2 times 2 is negative 4 plus 4 gives you 0, right? Okay, finally, the last one. What property do we use here? As you can see, the first row and the third row stay the same, right? Are the same. So what do we do here?
This is also property A, right?
Yeah.
Row 2 is you're subtracting minus 2 row 1.
Oh, I'm sorry, I just erased everything, but yeah, it's property A. So it's exactly what you said. So you multiply the first row by negative 2 and add it to the second row. So that gives you, so to the second row, you add this, right? So you see that minus 2 times 1 is negative 2. When you add it here, you get 0. You get this one. Then minus 2 times 3 is negative 6. When you add it to 0, you get negative 6. And then negative 4 times negative 2 is 8. 8 minus 3 gives you 5. And the others are the same, right? So let me rewrite what we had here. I think the first one was property B. The other one was property C. Then we had A, right? And then A. This was our conclusion for this set of exercises, right? Okay, now let's move down the list, and it's your turn again to choose either 5, 7, 8, 5, 6, 7, 8, one of these. 9, 10, doesn't matter. I mean, they are all the same. So let's avoid, long calculations. That's not the point. So let's say, either 5 or 6. So we don't have to calculate too much.
Actually, can we try 8, because I get a little confused on the longer ones.
8 is not very long. So let me move this thing here. So I have, the exercise, and let's do number 8. So you see now the notes, right? So let's go over number 8. This is from section 3.2, right? Section 3.2. And the problem is find the determinant by row reduction to echelon form, okay? So number 8, let me try to copy this determinant here. 1, 3, 2, minus 4. So we want to bring this into that echelon form. I mean, the matrix corresponding to this determinant. And we can do those operations because determinants have those 3 nice properties, and that helps a lot. So this is okay. 2. See if I missed any entry or I make an error. So this is negative 3, negative 10 here, negative 7, and 2. All right. So we want to bring the corresponding matrix into the upper triangular form. And then we know that the determinant of an upper triangular matrix is the product of the elements on the main diagonal, right? Okay, so this equals, and I need a longer equal. Okay, so I can multiply the first row by negative 2 and add it to the third row. So this is third row, R3, minus 2 times R1. If I do that, look what I get. Well, sorry for the not so straight line segments, right? I mean, vertical line segment. The first row stays the same, no problem. We don't change anything. Second row stays the same. We like it the way it is. Now, the third row, if you do this, so you multiply the first row by -2 and add it to this row, you end up with 0 here, right? That's the goal, to obtain zeros below except for the first element, for the first entry of the first column, all the others must be 0, right? Must be brought to 0. Now, this is -2 times 3 is -6 plus 7. I get 1. So it's -6 plus 7. Then you have -4 plus 6. This is 2. And then you have 8 minus 3. This is 5. That's nice. And now I'm going to do something, and I don't want to write, 10,000 times the same thing. I'm going to also do something like this. I'm going to multiply the first row by 3 and add it to the fourth row. So I'm going to do this, R4 plus 3R1. So the goal is to obtain 0 instead of this entry here, of the last entry on the first column. So this is 0, right? 3 times 1 is 3 plus -3 is 0. Then 3 times 3 is 9 minus 10 is -1. And then I have, 6 minus 7 is -1 here. 2 minus 12 is -10. So is this understood? This is allowed. The determinant is the same. Now this equals, I'm still not done. I want an upper triangular matrix, right? Or an upper triangular determinant, if you can call it that way. What should I do? This will be my new pivot, 1 here, this one. And I'm gonna do the following. From the third row, I'm gonna subtract the second row. Look what I get if I do that. So I get, I don't know why this is not straight. The first row stays the same, no problem. Second row the same, no problem. For those of you who are taking computational math with me, this is similar, very similar to the Gaussian elimination. Okay, now row 3 minus row 2. Well, 0 here. 1 minus 1, 0. 2 minus 2, beautiful, 0. Okay, and then what I have here is 5. It's 5 minus 5. This is 10. And here I have. Okay, let me see. Maybe I don't even. Yeah, I need to. I'm gonna also do the following. Row 4 plus row 2. I don't change the value. I can do it, in 2 steps. What for? To write more? I am not into that. Okay. So here it's row 4 plus row 2. This is 0. This is 0. Okay. 2 plus -1 is 1. Okay. And then row 4. Okay. Plus row -5 plus -10 is -15. Please follow, my calculations. I don't want to do any mistake here. Okay. Is this clear so far? Okay. We have zeros here. I want the echelon form. We just interchange the last 2 rows. Of course, when you interchange, we change the sign. So this is minus. So this is property B, the way we talked about those properties. So I'm using property B, and I'm going to interchange these two, the last two rows. And what's here is 1, 3, 2, negative 4. Then I have 0, 1, 2, negative 5. Okay, now here is 0, 0, 1 on the main diagonal, negative 15. And finally, the last row becomes 0, 0, 0, 10. Okay, what do we know about the determinant of an upper triangular matrix? Is the product of the element on the main diagonal, right? Just use the cofactor, expansion, right? So here so if you expand down this column, is just 1 multiplied this determinant, 3 by 3 determinant. Then that is multiplied by 1 by this determinant. Then multiply by 1 times this determinant. The determinant of 10 is 10. So this is just negative 1 times 1 times 1 times 10. So this is just negative 10. Is this understood? So you need a bit of practice to play with these rules, and and you can handle many determinants. Of course, by 5 determinants, or I don't know, higher, you need more calculations. The higher the order of the determinant, the more calculations you need. So the dimension is important in terms of calculation. We have MATLAB for that, or we have other software packages. But it's important to know how to handle these, let's say low dimension determinants, because this is the kind of application that you need all the time. Right? Is this understood?
So you just multiplied across the diagonal?
Yeah. So I mean, so for example here, right? You multiply the first row by negative. No, yeah. I mean, you mean for the last step, right?
Yeah.
Yeah. So that's because this is what you have for the last determinant. So how do you obtain this determinant here? 1, 3, 2. So this is a general property of upper triangular matrices. I can say it in general, but on this example, this is what we have. This is 2, 1, 0, negative 5, negative 15, 10, right? Well, if you, I'm sorry. If you use the definition of the determinant and expand along the first column, right? You have the first, you have the first element, 1, multiplied by this cofactor, T11. The others are not important because, along this column, all the other elements, so you have 0 times C, this is 2,1, plus 0 times C, 3,1, plus 0 times C, 4,1. So they are not important, right? These are all 0. The first one is important. So you have 1 multiplied by this determinant. Well, you can say, I'm not going to answer this. All right, so you can say, what's the cofactor here? You know that this is negative 1. Let me. To the 1 plus 1. And then you cross out the first row and the first column, and you obtain this determinant 1, 2, -5, 0, 1, -15, and then 0, 0, 10, right? Okay.
Yes. Okay.
Okay. Now you do exactly the same. So this equals 1. I'm gonna keep all these things. -1 to 1 plus 1. Of course, this is 1. And then you do exactly the same thing and you expand according to the first column here. So this is multiplied by 1, right? Then multiply by -1 to the 1 plus 1 and multiply by, so this is the cofactor C11 in this case. So this is multiplied by this determinant, right? Okay. Yeah. And then, okay, what's this one? It's 1 times 10. Okay, so this equals what? 1 times, I can, this is, I'm writing it again, 1 plus 1 times 1 times -1 to the 1 plus 1 times, this is 1 times 10. Okay, so these are 1. So what you get is 1 times 1 times 1 times 10. So these are the elements. This is 1, so I just ignore this one. This one is 1. This could have been something different, right? Even this one. It just happened to be just 1 in this case. That could have been something different. So that's why you have the product of the elements on the main diagonal. And of course, you change the sign here. So is this clear? I mean, that's why, so okay, I don't know if I wrote this or not, but I think we said that, right? We said that the determinant of, let me see if I did, if we said that. Otherwise, I'm going to say it again. Okay. I think, yeah. I mean, this is the proof. But this is what we said, right? This remark. If A is an upper triangular matrix, then the determinant of A is the product of all these the elements on the main diagonal. Same thing for the lower triangular matrix. It's exactly the same. It's still the product of the element on the main diagonal. And here, here was the proof. You see? This is something that we said last time, okay? Questions? All right, then let's move on. And let me tell you another, I can call it a theorem actually. It says that, this theorem says, okay, so where is that? Yeah. So if A is an n by n matrix, then A is invertible if and only if the determinant of this matrix is non-zero. Okay, that's very important. So if you compute the determinant of a matrix and that determinant is non-zero, then the matrix is invertible. And what's more interesting, the inverse of the matrix looks something like this. So here is the formula for the inverse of the matrix, of an invertible matrix. A inverse, that's the notation, is 1 over the determinant of A. So that's why the determinant of A cannot be 0. So if the determinant of A is not 0, then you can compute the inverse. And here, I'm going to write the adjoint matrix, which is really easy to define. So the 1, 1 cofactor is here, then is not the 1, 2, is the 2, 1 cofactor here. And then, 3, 1 cofactor. And here you have the N1 cofactor. Then you have this 1, 2 cofactor, 2, 2. So here is 3, 2, and 2, and so on. So here is the C1N, C2N. Maybe I should have written another one. C3N, CNN. Oh. Not better. Okay, so this is the inverse matrix. So let's do an example. So you can tell me, let's invert, a 3 by 3 matrix. You tell me the entries. Try to, small integers, because we don't want to calculate here forever. What you have here, this matrix here is called the adjoint matrix. The notation is this, the adjoint of A. Some books denote it by this, A star. And so this is the adjoint of A, right? And we can compute it, obviously. Okay, so let's take an example. Let's see an example. You tell me the entries, just a second. Let's say, let's take, a 3 by 3 matrix. So let's say this matrix A equals, okay, first entry, a number, a positive, let's, like I said, easy numbers. Any random, you can say anything.
1.
Okay, 1, that's good. Next.
Another 1.
Okay.
And then 3.
3, okay.
Uh,
We'll compute the determinant first. If the determinant is 0, then we cannot compute the inverse, obviously, right? The theorem is, okay. What here? Next entry?
2.
2.
0.
Okay.
1.
Okay. Don't be afraid of negative numbers as well.
All right. Negative 2.
Okay.
1 and 0.
Okay, perfect. All right. Let's compute the determinant first. So just let's make sure that we do have the determinant, right? So the determinant of this matrix, unless we were really unlucky, shouldn't be 0, right? In general, it's hard to get the value 0, but there are days and days. Okay, so here I can simplify a bit my life if I compute the determinant of this equivalent matrix. I mean, I can add that, I can add the second row to the third row. I don't change anything if I well, let me see. Maybe I can do better. I already have, here I have a 0 here. Maybe if I multiply the first row by -2, so I'm going to multiply the first row by -2 and add it to the second row, right? So the second row, so this is what I'm going to do. R2 minus, no, this is not a good idea. So how do I want one more 0. Let's say on this one. I can multiply I can multiply by the first row by -1 and add it to the third row. So third row minus the first row. Okay, so nothing changes in the first 2 rows, but here I have -2 minus 1 is -3. Here is 0, right? That's the goal. And then you have here -3, okay, plus 0, this is -3. I'm going to expand this determinant down this column, right? So this equals 1, this is the element 1, multiplied by this cofactor, C, 1, 2. All the other cofactors are 0, right? Because you have 0 multiplied by C2, 2, plus 0 multiplied by C, 3, 2, right? Third line or third row, second column. So these are 0. So this is 0. This one is 0. And so all we have to compute is this one. It's 1 multiplied by, okay, what's this? C1, 2, it's -1 to the 1 plus 2. And now I have to cross out the first row and the second column. And if I do that, obtain this, the determinant of A1, 2, right? You know, that, remember that notation. This is 2, 1 here, -3, -3. Okay, so I think we are in good luck today. So this is 1 times -1, well, to the 3 is -1, so this is negative. And here this determinant is -6 plus 3. Okay, so this was a good choice. In the end, we get the determinant equals 3. So the determinant of A, of this A, is 3. Did you get the same? You can compute it in many other ways. I mean, this is just one way to compute the determinant. Now, let's compute the inverse. So for that, we need the adjoint, okay? So what's the inverse? It's 1 over the determinant of A, according to our formula. And here is the adjoint. We need to compute all these numbers. C11, C12, C13, and then I have here C21, C22, C23, and finally I have here C31, C32, C33. Okay, so now all we have to do is to compute these numbers. I'm going to compute not all of them because it's boring, but let's compute C11. This is -1 to the 1 plus 1. That's the definition. And then you cross out the first row and the first column of the original matrix and take the determinant of what's left. So this is 0, 1, 1, 0. Okay, so what do I have here? -1 squared is 1, minus 1. So this is -1. I got the first element, the first entry. So this one is -1. Tell me which one, what other entry you want me to compute. I'm not going to compute all 9 of them, obviously. Another entry of this adjoint of A. See?
3, 2.
3, 2. Very good. 3, 2. Okay, so this is -1 to the 3 plus 2. And now we cross out the third row and the second column. So the third row is this one, and second column. And what's left, okay, it's 1, 2, 3, 1. Third row, this, second column, this. And then you have, this and this. It's in the matrix, but, you understand. Okay, so what's this? So this is -1 multiplied by 1 minus 6. 1 minus 6 is -5. This is 5. Okay, so if you compute all of these cofactors, and then you have something like this, it's 1 over 3. We computed only 2, so I'm going to replace this here, -1, here, I don't know. We didn't compute it, didn't compute it, didn't compute it, didn't. Well, we did. Didn't. You understand how to compute the inverse of a matrix by hand. This is what you have to do. Okay? And it's essential that the determinant is non-zero, otherwise you don't have an inverse. That's what the theorem says. Okay, another thing. Questions. You can ask me questions anytime. Okay. For a matrix A, so let's say you have a matrix A, which is this, n by n matrix, A11, A12, A1n, I don't know, somewhere here, AI1, AI2, let's say AIJ, AIN, AN1, AN2, and so on, ANJ, ANN. You can define the transposed matrix A sub T. This is the notation, the transposed matrix of A, the transposed, so this is the transposed of A. Transposed of A. In this way. Okay, so you have A11 stays the same, but then here you have A21. Here you have A12. You see the rule, A22. Here you have A1I, AI1, AN1, A1N. You just revert, the indices. A here, 2I, AJI, ANI, and so on, ANN. So the idea is this. For you obtain A so from A, you obtain A transposed if any n entry of A, Aij, becomes AJI, right? So for example, if you have this matrix, let's say you have this matrix, A equals 7, -9, 3, 0, 2, 4, -1, -2, -7. Then the transposed is just this. 7, 0, -1. As you can see, these are the elements of the first column on the first row of the transposed. Then you have 9, 2, sorry, negative 9 is here, right? Negative 9, this is negative 9, 2, and negative 2. And then you have 3, 4, negative 7. You see the transpose. You see that? It's just a reflection about the first diagonal, the main diagonal of matrix, of the entries in matrix A. So you obtain A transpose by reflecting about the main diagonal, the entries of A. Right? It's easy to see that. Okay? Now, there is an important theorem relating A and A transposed, which says the following. If okay, so let me state it. So we assume that let A be an n by n matrix. Then the determinant of A equals the determinant of A transposed. Okay, so comes from the proof is very simple, comes from the very definition of a determinant. I can convince you that that's the case in our example. So let me convince you that this is the case for our example. So we'll get to compute more determinants in this way. So you compute the determinant of A, and I'm going to compute the determinant of A transpose. And let's see if we get the same number. Okay, I'm going to compute the determinant of A transpose for our example, for this example.
Yes.
And you compute the determinant of A, and let's see if we get the same number. Okay, we should. Okay, so I'm gonna be a little bit, quiet. I mean, I'm gonna be quiet, and compute this. You do the same calculation for A, right? I got 0. Did you get 0 too?
I'm still trying to solve it.
Mhm. Okay, so let me use MATLAB so I can confirm, or let me move it from there here. So I have this matrix is 7 minus 9, 3, 0, 2, 4. Yeah. What did you get? Did you get 0?
Yeah, I got 0.
Okay, let me show what MATLAB gave us. So that's why, I said computers are dumb in computational math. This is 10 to the negative 15. See, it doesn't give you the exact value because of those errors. And think about this is just, let's say, a 3 by 3 matrix. Think about the errors that you have when you compute the determinant of very large matrices. So that's why computing inverses is very expensive from the point of view of calculations. Okay, so you compute inverses in a different way, not just by computing, the determinant of the matrix and the adjoint matrix. Okay, but that's a different story. Anyways, we got the same thing, right? So we got, so if okay, so this is the determinant. Okay, let me just of A as well in this case. Okay, cool. Now, so let probably I convinced you that this is indeed the case. Of course, you can have a formal proof for that. I'm not going to give you that though. Let's move on and let's talk about other properties. Well, another one is that if another theorem is that if you have two matrices, so let's say if A and B are n by n matrices of the same dimension, in other words, then the determinant of the product of these two matrices is the product of the determinants. It's a very interesting and useful property. So this is an important property, and we can test it by considering matrices. I mean, for example, I'm going to consider a very simple matrices. So let's say 2 by 2. So we won't have to compute too much. So this is, let's say, -2, 1, 3, 1. Okay. And then B, I'm going to say that this one is 1, -2, 0, 7. Now, okay. So what's A multiplied by B? We know how to multiply matrices. The first entry is -2 times 1. So -2 times 1 plus 1 times 0. That's the first entry on the first row. Then you have negative 2 times 1 multiplied by the second column. I mean, the first row multiplied by the second column in this way. So negative 2 times negative 2 plus 1 times 7. I'm done with the first row of this matrix. And then I have 3 times 1 plus, so the second row multiplied by the first column of B. So the second row of A multiplied by the element-wise, and then you sum up these multiplication. It's like, the scalar product, okay? Now here you have 3 times 1 plus 1 times 0. And you have 3 times negative 2 plus 1 times 7. Okay, so A multiplied by B equals this 2 by 2 matrix, obviously. So I have negative 2, 4 plus 7, 11, right? Then here I have 3. And if I haven't made any mistake, this is 1. Did you get the same? Now let's compute the determinant of this product. Uh-oh, what happened? That's not good. It seems like, it's Zoom. What happened here?
You can try and click the arrow in the top left.
This one, top left. Undo. Thank you. Yeah, probably I can undo. Okay, thank you. Yeah, so this works. I don't know what I probably this pen has those buttons and I click on something by mistake. Okay, so what's the determinant of this product? Is negative 2 times 1, right? Negative 2 times 1 minus 3 times 30 times 11. So this is negative 35, right? Now let's see the product of these two determinants. The determinant of A, which is what? I can write directly. This is negative 2 times 1, negative 2, minus 3. So this is negative 5, right? And the determinant of B is just 7. And you observe that the product of these two determinants is what? Is negative 5 times 7 is the same thing, right? So this is indeed a true property, okay? Questions about this? So this is again an important and interesting property of the determinants. The determinant of a product of two matrices is equal to the product of the determinants. Now, another one is related to the linearity property, which is also important. So let's talk about a linearity property. Of the determinant. Well, I'm going to follow what they said in the textbook. And the idea is this, in fact. It's I'm going to just write, the linearity property. Maybe I'm not going to follow that because, it's kind of cumbersome. So it says the following. So you have the determinant of this matrix. So these are columns, right? So this is the first column. It's an n-dimensional column vector, A1. A2 is the second column of this matrix, right? And here, let's say, on the Then you have the j minus 1 column is this one. And then you have here, let's say, constant c multiplied by, let's say, this column. So this is your column now. It's a constant c multiplied by this vector x, which is a column vector as well. Then a j a n, the last column. Well, this equals c times the determinant of a1 aj minus 1 x. So c pulled out aj, the next one a n. I'm going to exemplify this. We already talked about this. I mean, I think it was property c when we talked about properties of determinants. It was for rows, but it's true for columns as well. Whatever is true for rows is true for columns, and vice versa, in general. Because because of the fact that the determinant of a matrix A equals the determinant of the transposed of A, in general. Okay, and the other part of this linearity property is this one, that the determinant of A1, A2, aj minus 1. Let's say here on the jth column, you have u plus v. Then aj, an. This equals the determinant of a1 aj minus 1 u j minus 1 here, I don't know it, aj an plus the determinant a1 and so on aj minus 1 v, okay, aj plus 1 here. I think I should have said plus 1 everywhere. Plus 1 here, plus 1, and we jump over plus 1 here. Okay, plus 1, we jump over j, right? The jth column is this one. Okay, j plus 1 here. All right, an. This is the so-called, I mean, these two together form the so-called linearity property of the determinant. So let me give you an example because it's much easier to understand through examples. It says the following. I'm not going to read the chat. I mean, I don't have time for that, but you can ask me, directly. So it says the following. It says, if you have here 1, let's say here is 2 plus 3. I'm going to write it like this. Then here is negative 5. Then, I don't know, 0, negative 1 plus 6, 7, 3, 2, plus 9. The last property, 7 or negative 9, let's say. This equals 1, 2, negative 5, 0, negative 1, 7, 3, 2, minus 9, plus 1, 0, 3, nothing changes here, but here you have 3, 6, 9, negative 5, 7, negative 9. So this is what the second property says. Okay. And same thing goes for any row or column. So if you can split, a row or a column into a sum of two vectors, then you can split the determinant this way. And the first property says something like this. Let's say you have 1, 0, 3, I don't know, here 3 times 5, 3 times negative 2, 3 times 11, and here is minus 5, 7 minus 9. This equals 3 times 1, 0, 3, 5, negative 2, 11, negative 5, 7, negative 9. Is this clear? These are important properties of the determinant. So if you play with these properties, you can pretty much compute, all, let's say, lower dimensional determinants. In principle, you can compute any determinant. The problem is with the volume of calculus, the number of calculations. Okay. So this is an exemplification. Let's say this is 1, property 1, and this is 2. So here is 1, and here is 2. I exemplified, these two properties. Okay. All right. Now, one more thing which I would like to cover before we finish this lecture. Let's talk about Kramer's rule. It's a very important rule, and I think this is section 3.3 in your textbook. So let's talk about Kramer's. It's not the Kramer from Seinfeld, like I always say. Kramer was a serious German mathematician. So Kramer's rule is designed for solving systems of this form. A matrix A. So let me write it like this: A11, A1n, AN1, ANN, times a vector x, x1, xn, equals vector b, whose components are here. Of course, if you want, you can write this in matrix vector notation as A. So this is A times X. This is X. I'm going to put, this little arrow above X to symbolize that this is a vector. And this one is B. So in matrix vector notation, this is what you have. And you want X. You know A and B. You want X. Okay. Here is Kramer's rule. So we introduce a notation first because we need that. Makes things easier. So I'm going to introduce this notation. A, I, B, like in the textbook. And this is the following matrix. The first, all columns are the same as in matrix A with a difference. So A1 stays the same. The first column stays the same. The second column stays the same up to the I-1 column, which stays the same. Then you replace column I by this vector B, the right-hand side of the equation, column vector. Then here you have AI plus 1, A sub n. So you understand, right? You just replace the ith column. So this is column I, right? By this vector B. And then Kramer's rule says the following. Says that the components of the solution, so the entries of the solution, X, have this formula. The determinant, this is the quotient of the determinant of A, I, B of this matrix over the determinant of A. It's a very interesting and fast rule. Of course, the matrix A has to be invertible, otherwise the determinant is 0. You don't divide by 0, right? Let's see an example before we leave. A simple one, so we don't have to compute a lot. Let's say we want to solve this system. 2x1 minus x2 equals 3. And then I can say minus 7x1 plus 3x2 equals 4. Okay, so in matrix vector notation is 2, negative 1. The same system, it can be written as follows. Minus 7, 3 times x1, x2 equals 3 and 4. Okay, this is our matrix A, and this is B, our vector B. Of course, this is what we called X. So AX equals B. Now, Kramer's rule says that x1 equals the determinant of A. That's easy because A is there, is 2, 7, negative 1, 3. But here you have the determinant of A1B, which in our case you replace the first column by the column of the free terms on the right hand side. So by B, right? So you have 3, 4, and then negative 1, 3. Of course, you can compute this. This is 9 plus 4, 13, our lucky number, right? And here you have 6 plus 7. That's nice. 13. So I lucked out. This is 1. And x2, by Kramer's rule, here you have the same determinant, which is 13. We already know that. Oh, actually, it's minus 7 here. I'm sorry. I didn't notice this. So probably this one is not. What do I have here is 6 minus 7. Okay, just let me erase this. I didn't pay attention to this sign. Obviously, this is not true. Okay, so this is negative 7, right? Okay, so I have 6 minus 7. This is negative 1. So this is negative 13. And x2, okay, is the same. So this is negative 7, 3 here, and here have 2, negative 7. You replace the second column by the vector B. Okay, so this was this then. It's 8 plus 21. All right, and here is negative 1 again. Okay, now let's verify this result. You can verify this in MATLAB. That's easy. So do I understand the method? I mean, what we did here. This is the same thing. I mean, you can do the same for 3x3 systems, for any kind of systems. I mean, square systems, n equations, and unknowns, and make sure that the matrix of the system is invertible, meaning the determinant is non-zero, right? Okay, so let's see this one. I'm gonna use MATLAB to show you something. I mean, show this. I'm gonna type, the matrix A first. I'm gonna show immediately that thing. So A is 2, -1, and then -7, 3. If you have something to say, like I said, don't chat. I mean, unless you want to chat with your friends. I should have disabled that. But otherwise, just tell me if you have any questions or anything. I can answer them, in real time. Okay, so I introduced A and B. So this is the matrix of our system. This is the vector B. And then you can use MATLAB. You can find the solution by using this built-in function. So I'm just trying to check, the answer. And the answer is correct, -13 and -29, right? Okay, guys, I think we've had enough fun for one day. And obviously, if you have questions or anything, you can ask me, now, or email me, or even better, ask Norma, or yeah, Christopher.
Can you hear me?
Yeah, I can hear you. Yeah.
Okay. Going back to that first problem we did, number 8 from section 3.2.
Okay. Let's see.
Is the determinant -10 or +10?
Let me see where that is. Yeah, it's -10. Because here, after that, we computed just the determinant without this negative sign in front of it. When we interchange the rows 4 and 3, or 3 and 4 here, we change the sign.
Okay.
That's property B, like we said here, right?
Right.
All right.
Right.
So then, yeah, it's -10. That's the correct answer.
That's why it's negative. Okay.
Yeah, that's why
I got it.
because of this negative sign here. And then here we computed in just the determinant, and we got 10.
Right.
I just illustrated how to show that if you compute the determinant of an upper triangular matrix, the determinant is the product of the entries on the main diagonal, right?
Right. Okay. Right.
Okay.
I got it.
Sure.
And,
Thank you.
someone in the one more thing, please. Someone in the chat is asking, where are the lectures posted?
Well, I sent the links to Norma. I don't know, Norma didn't answer. I think she'll answer my emails, and but I cannot. She'll post the links, and I send the videos, and I'm gonna send the PDF files of these notes as well. I mean whatever we have here. I don't know if that's useful to you or not, but you can see them probably. I'll make PDF files of these notes and send them to Norma as well. Norma is a very diligent instructor, and I know she's well organized, so it's not a problem. She'll post all these things soon. Okay.
Okay.
This is really important stuff. I mean, trust me, it's not because I substituted for Norma or anything. I mean, this is about solving systems. And of course, you can use the echelon method. You can use the other methods, substitution method, naive Gaussian elimination. There are other methods, but Kramer's rule is very, I don't know, easy to use and fast. I mean, you can look what we did here. Usually, especially in differential equations, you end up with systems like this. You can, immediately find the solution. It's very. Otherwise, you can use the substitution method or the elimination method. Like I said, there are so many, but this is fast one. Kramer's rule, for example. And those things about the determinants, are really important. Like we covered the all important properties of the determinants. Of course, knowing how to move, the chess pieces doesn't make you an international champion. So you have to practice this thing. I mean, do as many examples from the textbook as possible. Try to compute those determinants, and you'll get, used with them, familiar with the calculations and operations and properties of determinants. Okay.
Okay.
All right, guys. So I think that's it for today, and have a nice evening and weekend and everything. Okay.
Take care.
Bye.